The question that I have is, what are the factors that affect the value of permeability of soil? An equation that is very useful for understanding the factors controlling permeability is the Kozeny-Kármán equation. And according to this equation, permeability is a function of all these variables. And we have G in here, which is the gravitational acceleration. C sub S is called the particle shape factor. It's about 360 for spheres and about 700 for angular particle. Rho sub W is the mass density of water. Mu is the viscosity of water. Capital D here is the characteristic diameter of soil particle. And E is the void ratio. Let's say we have a soil saturated in water. I can pack the soil in two different void ratios, right? So to see the influence of the void ratio, I'm going to write the equation in this form. I'm going to lump all of these factors into a constant called C and then leave the term involving void ratio as is. And here I am calculating the value of K1 at two different void ratios, 0.6 and 1.2, and I got these values. So when E2 over E1 is 2, K2 over K1 works out to be 5.8. In other words, I change the void ratio by a factor of 2. Permeability changes by a factor of about 6. So you can see that the void ratio definitely has a very strong influence. The looser the soil, the higher the permeability. Similarly, to look at the influence of the particle size, let's say we have two different soil at the same void ratio and at the same values for all of the other parameters. Then we can write the Kozeny-Kármán equation in this form, K equals C times D squared. Let's say we have two different sand. One has a particle size of 0.2 millimeter, the other one has a particle size of 0.4 millimeter. Then the ratio between the two permeabilities works out to be 4. In other words, you double the particle size, the permeability increases by a factor of 4. So what happens to the permeability as we go from sand to clay? So let's consider a third soil that has a particle size of 2 micron, which is representative of a clay soil. The permeability then works out to be 4 times 10 to the minus 6 times C. So as we decrease the particle size by a factor of about 100, then the permeability decreases by a factor of 10 to the minus 4. So this analysis kind of tells us that as we go from sand to clay, the permeability could decrease drastically. And in fact, this is the case. Here is a list of the ranges of permeability values for different types of soil. For gravel, it's greater than 10 millimeter per second. For sand, it lies between 10 and 10 to the minus 4. For silt, the range is between 10 to the minus 4 to 10 to the minus 6. The permeability of clay can be less than 10 to the minus 6 millimeter per second. So you can see as we go from gravel to clay, the permeability decreases by more than a factor of 1,000,000. So far we've talked about the influence of the void ratio and the particle size, right, in terms of diameter. There are obviously a few other parameters in this equation, including the density of the fluid. And here we called it rho W because we were considering water, but if you have a different fluid, it may have a different density. So that comes into the equation. The viscosity of the fluid, mu, and the shape factor of the particles, right? So if you have a different fluid, such as, for example, oil, we know the density is about 90% of the density of water. Viscosity is much higher than the viscosity of water, right? So they should be properly accounted for. Your value of the permeability will reflect that. For the same fluid, we know the viscosity is usually very sensitive to the temperature changes, right? Usually when the temperature goes up, the viscosity decreases, And since K is inversely proportional to the viscosity mu, K increases. This is the reason why every time we evaluate a value of permeability for a soil, we normalize it with respect to the ratios of viscosity in order to express the permeability at a standard temperature of 20 degrees C. Here is the equation for doing that.